Okay, good afternoon, everyone. So in my first two lectures, I tried to make two main points. One of them is that we have various ways of characterizing the behavior of many body chaotic systems. And the second point was that by thinking about random quantum circuits, we have ways in which we can actually do calculations. So what I want to tell you about in this lecture is three calculations which get at the quantities I was talking about in the first and second lectures. So first of all, I want to talk about calculations of the spectral form factor, which, as you remember, tells us about correlations in eigenvalues. And originally, one thought about eigenvalues for Hamiltonian, but as you saw, when we're thinking of quantum circuits, we're thinking in the language of evolution operators. So these will be eigenvalues of a Floch A operator for a Floch A random circuit. And then after that, I'll talk about entanglement spreading and operator spreading. And the details of the random circuit won't be so important in the way that I described these last two calculations, but I'll be following work that was done for models of circuits which are random in time, so that instead of having something Floch A, which is periodically repeated in time, the gates that make up the circuit are chosen independently, and so we have circuits that are random functions of time. So in all these calculations, the basic idea that you're following when you construct the quantum circuits is, as I said, that it would be hopeless to try to do a calculation for a specific chaotic quantum system. But what we can hope to do is study an ensemble of systems and try and calculate averages over that ensemble. And when we try to build models which have spatial locality built into them, then we do that using gates that act locally, and it's those gates that we choose to be random. And so a basic element in all of these calculations is going to be averaging over different choices of one of those gates. And since they're gates describing time evolution in quantum mechanics, they're represented by unitary matrices. And so what we need to be able to do is average unitary matrices over a distribution, and the distribution that we'll be using is the one that's uniform on the group, the one that's known as the Haar measure. So the foundation for anything that happens later on has got to be talking about averages of elements of an n by n unitary matrix and averages of products of these over the Haar measure. And to an extent, the result when you do those averages is known. And so I want to talk a little bit about it. But the result looks pretty off-putting at first. So let me try and walk you through some of it. So to repeat on the board what's on the slide, we're thinking about an average of elements from U and from the complex conjugate So I'm using labels A and alpha on U and B and beta on the complex conjugate. I'm writing the average right now. So the first point is that this average involves lots of Kronecker deltas, this one out the front and the ones that are written here, and then something which actually depends on the choice of indices if the Kronecker deltas are all unity. So what's the reason for all these Kronecker deltas? Well, even before you think about the entire Haar average, you can see that there are some invariances in the ensemble. So, for example, we could multiply all of the matrices by some common phase, and if we average uniformly over this phase, then we're doing part of the Haar average. And clearly, when we have some number of factors of U and some number of factors of U star, unless the two numbers, which here are M and N, coincide, then these phases won't cancel, and the average over that phase will be 0. So that's the reason for this Kronecker delta up the front. But you can do more than that. You can take a U and multiply by phases which depend on the row and the column. So I can multiply it by a phase phi A and a phase phi prime alpha, and average uniformly over these phases phi A and phi prime alpha, and that again would be doing part of the average over the Haar measure, and again we'll get 0 unless the phases pair up. So what this means is that the sequence of labels A1 to AM, which is now the same thing as the label N, that must be some permutation, call it say sigma, of the labels in U star, B1 up to Bm. And in a similar way, the labels A1 to alpha 1 to alpha M must be permutation, call it tau, of beta 1 to beta M. And provided you satisfy those conditions, then you get a non-zero average, and the average depends on what these permutations sigma and tau actually are, and also what the size of the matrix is, and all that dependence is hidden in this quantity at the end, which is called a Weingarten function. So in a sense, writing this down doesn't tell you much until you know these Weingarten functions. And for low order, low numbers of U's and U stars, they're tabulated, and going up to about 20th order, you can construct them using computer algebra. But beyond that, this expression is not really useful in practical terms. So when it's simple is when either the order is low or the size of the matrix is large. And the lowest order, of course, is when we have one U and one U star, and in that case, the labels have to be typed together in the obvious way, and the value of this average is just 1 over n, which you can convince yourself easily by thinking of these elements as elements of a normalized vector. And the other limit where things are simple is when the size of the matrix is large, and then the different elements of the matrix are to an approximation that gets better and better as n gets larger, independent Gaussian complex random variables with the magnitude of their fluctuations fixed by this first result. And if you, this is lowest order, if you go to next order, then you get something that looks a bit complicated to digest, but basically there's something which is 1 over n, and there's something that's subleading. Actually, I forget whether this is right. It looks as if it perhaps ought to be 1 over n squared, but anyway, this is subleading. And just to unpack that last one a little bit, because we'll be using it, if I think about an average U A1 alpha 1, U A2 alpha 2, and then U star B1, B21, U star B2, beta 2, and I average that, then if these were completely independent Gaussian random variables, then you'd use Wick's theorem and you'd think of these two labels as being a single object, and you'd say that you compare this with that, say, and this with that to get a non-zero average, or alternatively, you could pair it the other way with this with that, and this with that, and the top line here represents just that kind of pairing, and the bottom line, which is smaller, and then represents more complicated ways of lining up the pairing of the indices. So anyway, yes?
So you currently something like 1 over n, but it should be 1 over n from the first line because the permutation is this. The sigma down to minus first is identical, so
yeah, I mean, I'm worried that because we've got another 2 powers here.
But the argument is the product of permutations, and both permutations are swaps of 2
It
indices.
should be n squared minus 1 instead of 1 over n.
Yeah, sorry, you say it should be?
It should be 1 divided by n squared minus 1.
Yeah, I think that's right, yeah. Yeah, okay. As a basic point is that we've got more powers here, so it should be smaller than that. But anyway, there is most likely a misprint on the slide, but that's not really the central point. I wanted to give you some sense for how details of the calculation go, but of course, in the rest of the lecture, I'll try to avoid all these details. So, to give you not quite such a detailed impression, but a moderately detailed impression of a calculation, I wanted to talk first of all about calculating the spectral form factor for the case where we don't have an entire quantum circuit. We simply have, we're thinking of this evolution operator as being an n by n Haar random matrix. So we we want to evaluate the spectral form factor in terms of the eigenvalues, but as I was saying yesterday, that's also the average of the modulus squared of the trace of the evolution operator. And if we expand the trace of the evolution operator raised to some positive integer power t, because we're thinking of t time steps, then we have matrix elements with sums over labels, and we can represent that as some kind of closed path, closed because it's a trace, where the, actually I should shift the labels A, because the dots represent the factors of W, and then the links represent contractions, and it's the links that carry the labels A. So the question is, what will contribute to the average? And the point is that if we have a sequence like this contributing to the trace of W with particular values for the labels A1, A2, and so on, and a similar sequence contributing to the trace of W dagger with labels B1, B2, and so on, then the two terms will interfere with each other constructively, meaning that the phases will cancel if the path in this lower sequence is the same as the path in the upper sequence, so that we have W times W star, and so on. Or equally, if the path in the lower sequence is a time-translated copy of the one in the upper sequence. And this is a kind of central idea, which is going to be important for all of the calculations I talked about. So you can represent that idea in terms of pictures. If I simply have the two paths have indices that line up, I have a picture which I've drawn here, and if things are shifted, then the links between the points that represent the matrices and matrix elements W and W star, these lines between them will be shifted in a way that appears in later pictures. So if you go into more detail, then if we think of a combination of an element of W and an element of W star, we can draw them in this way. And what I was saying about averages is that, well, if these are exactly Gaussian distributed, then the result of doing the average is that the indices have to be equal in pairs. So instead of AC and BD, we have AA and BB, and then we have a factor of 1 over n associated with this dashed line. And so before averaging, we represent these two traces with a picture like this, where the blue lines have periodic boundary conditions on them, and likewise the green lines. And then after we average, one possibility is that we pair things up in this way, and then instead of having independent labels A2 and B2, we have the same label on the blue line as on the green line, and so on, respecting these Kronecker deltas. And then if you think about working out the contribution of this diagram to the spectral form factor, well, on the one hand, for each time step, we've got one of these averages which carries a 1 over n. So after t time steps, we've got n to the power minus t, but we've also got sums over these paired indices, and there are t of them. So when we carry out these sums, the final contribution from what's represented here is unity. And of course, there are other contributions because, as I was saying, we can pair either directly or in a time-shifted way. So shifting one time step, we get a diagram like this. But again, each label is equal. Each label on the blue line is equal to a paired label on the green line. And when we combine the factor of 1 over n to the t with the sums, we get a contribution of 1. And then to get a sense of what we're neglecting, well, on the one hand, we're neglecting something which I said was subleading at large n to do with higher averages. If we approximate these matrix elements by taking them to be exactly Gaussian, so those one kind of subleading contribution, and there's another kind of subleading contribution from the way that we pair up these Gaussian averages using Wick's theorem, because, oh, I'm sorry. Okay. Something that, okay, there's something that's not coming out on this slide.
I think it comes.
No, I think maybe I need to. Right, this is what I intended to show. So, thinking of Wick's theorem, an alternative to this pairing would be the one that I've drawn at the bottom. But if we pair things up in that way and use this rule with Kronecker deltas, then when you work things through, you find that instead of having 3 independent labels on these central legs, you just have a single label. But on the other hand, we've got the same number of pairings in both diagrams. So we've got this factor of n to the minus 2. But because these labels are all the same, instead of having 3 independent labels, we've got 2 fewer sums over indices, and that leaves this contribution suppressed by a factor of n to the minus 2. So the outcome is, at large n, that we have these t different pairings, and they each contribute unity to the spectral form factor. So altogether we have a spectral form factor that's linear in t, as I said it should be when I was talking about eigenvalue correlations. So in this way, if we go back to the behavior that you can work out exactly for the circular unitary ensemble, then you reproduce this linear slope. But because we were taking the large n limit at fixed time, that sort of pushes the plateau here off to long times, and in fact the existence of that plateau is not something that you can get from this kind of protective calculation. Okay, so I was reasonably detailed there, but I'm of course going to be more sketchy now, and ultimately I want to talk about calculations of 3 quantities, and now we're at the stage of talking about the first one, which is the spectral form factor, not for this toy problem of a single random matrix, but rather for quantum circuits. And the ideas that I've described to you were extended to quantum circuits in a series of papers, partly from the group here and partly from people I was working with. So I hope that in the lecture tomorrow you'll hear from Thomas Presen about the corresponding calculation for dual unitary circuits, which uses this idea of dual unitarity, but doesn't rely on any of the large Q ingredients that I've been talking about. And what I'll sketch to you next is a large Q calculation for a Floquet quantum circuit, and it's a particular one with variable coupling strength between the sites that I mentioned to you at the end of yesterday's lecture, and that I'll describe again. And that's chosen in order to reproduce some features of the spectral form factor that I believe are quite generic and that can get lost in other large Q calculations. So the basic question is, what could there be that's different in many body systems compared to the calculation that I talked you through for a single matrix from the circular unitary ensemble. And the basic idea in the single matrix calculation was this one that I've emphasized repeatedly of pairing up the path that contributes to the trace of the evolution operator W to the power T, and the one that contributes to the trace of its emission conjugate. And what can happen in a many-body system is that you get different spatial domains, and in those domains, within the domain, you have one type of pairing, but the nature of the pairing is different from one domain to another. And as I'll say in a little bit more detail, there's a statistical cost for the domain walls between pairings. And since you have t possible states within a given domain, you've got an equivalence to a kind of model which is known in classical statistical mechanics, where on each site of the system, that's to say each site in space here, you have t possible states corresponding to the different possible pairings, and if adjacent sites are in different states, then you have a statistical cost for that kind of domain rule. Yes?
What quantifies these regions and what causes the domain walls?
Well, in general, the idea is that you sum over lots of contributions to the spectral form factor, and those contributions will include some in which there are what I'm calling domain walls. And then the question is whether the contribution, whether those contributions are important or not. And I'll hope to make that a bit clearer in the next few slides.
Why did we have that before?
Well, because before we were just thinking about a single unitary matrix, whereas here we have gates distributed in space. So the way you pair things on one sequence of gates might be different from the way that you pair things on a different sequence of gates.
Maybe it will become clearer.
Yeah, let me go over a couple more slides, and I hope it'll become clearer, and if it's not, please ask. Okay, so this is the model that will be behind what I talk about, and I mentioned it briefly yesterday. So again, this is a picture with space horizontal and time vertical, and on each of these sites, I have a Q-dimensional local Hilbert space, and what's drawn here is the flock A operator for a single time step, and it has 2 bits to it. So firstly, independently on each side, I do a unitary rotation represented by these shaded circles. And then as the second part of the time step, I have some coupling between adjacent sites with a diagonal matrix with phases that depend on the states of the sites. And I can use these, for example, to be Gaussian random variables, and the only thing which will matter is their variance, which I call epsilon. And the crucial point is that this gives me a tunable strength to the coupling between sites, because if I set epsilon to 0, so that all these phases are 0, then this second layer is just the identity matrix and the sites are uncoupled. But if I make this epsilon large, then there's some kind of coupling between the sites. Then what we want to do is think about pairing, about possible contributions to the trace of the evolution operator, that flock A operator that I'm representing again here, raised to some integer power t. And so I can write out a path now in Fock space that contributes to the trace of W, and a path, again in Fock space, contributing to the trace of the complex conjugate. And I want to pair labels in the way that I've been talking about in order to get constructive contributions and constructive interference. And if I think, first of all, about these single-site unitaries, then I can make that pairing in a given way on one site, and either in the same way on the neighboring site, or perhaps on the neighboring site with some time shift. So we can represent these possibilities in pictures like this. So if I pair in the same way on adjacent sites, then if you look at the details, these coupling phases cancel, and so we get a contribution to the spectral form factor, which remains the same even if regardless of the strength of the coupling between the sites, the strength of this parameter epsilon, which describes the fluctuations in the coupling phase. But on the other hand, if when I pair labels in W and W star at adjacent sites, I take different pairings, then it turns out there's no cancellation of these phases, and you end up with a statistical cost, which grows in time because for each time step we have an extra contribution from these phases. So what that means is, well, if this coupling strength is small, then at short times this statistical cost is not very important, and at long times it becomes important. So at short times you might as well have all the sites of the system uncoupled, and for a single site the spectral form factor would be simply T, but if you have L sites in the system, then the spectral form factor grows much faster. It grows like T to the L. But at long times, these couplings become important, and what survives is just contributions where the pairing is the same at every site, and so we get back to the behavior of the spectral form factor that we would have for a single unitary random matrix. And as I was saying, that gives us an exact mapping to this classical model called a T-state hot ferromagnet, where we have classical variables on each side which take values from 1 to t, and the energy of interaction between neighboring sites is 0 if both sites are in the same state, and there's an energy cost if the sites are in different states. And inverse temperature times this energy scale in the statistical mechanics language is the same as this coupling strength epsilon times time in the chaos language. And in fact, there's an equality at large Q between the partition function for this Potts model and the spectral form factor. So when epsilon t is large, that's like going to low temperatures, and then what contributes to the Potts model is just ground state, and since there are t ground states, the Potts model partition function is t, and that's the behavior of the spectral form factor at low times. But at high temperatures, when epsilon t is small, we can have each site contributing independently, and so the partition function of the Potts model gets a factor of t for each site, which gets you back to this time to the power L in the spectral form factor. So if you work out the behavior of this Potts model partition function as a function of time, then for different system sizes, you get pictures like this. So as you make the system size larger and larger, this contribution at early times gets bigger and bigger, but at late times, you simply have the same behavior for the spectral form factor as for a single unitary random matrix. Now, this is a calculation for large Q, but of course you can also do numerics for finite Q, and these are results for Q equals 3, with again curves for different system sizes, but here we're using system sizes from 4 to 10. So if you look at the smallest system size, then as a function of time, the spectral form factor shows the ramp that I talked about in the case of a single random matrix, and then a plateau at late times. And the switch from the ramp to the plateau happens, as I said, at the Heisenberg time, which is set by the dimension of the Hilbert space for the system. And so it grows exponentially with system size. It's L to the power Q. So for this smaller system size, the Heisenberg time fits on this picture, which is a blown up version, I think. Sorry, it's a picture which goes out to late times. This is probably for for the very smallest system size, this line in blue, the Heisenberg time is here. I guess that's for n equals 4, and probably this picture is n equals 5. And then when we go to larger values of L, this enhancement of the spectral form factor at early times shows up in the numerics at finite Q, just as it shows up in these large Q results. So there's a time scale in the system where we go from something that reflects spatial locality in the model to behavior that's the universal form that we expect from random matrices. Okay, so that's what I want to say about calculations of the spectral form factor. And now I'll switch to, well, first of all, calculations of entanglement entropy. Are there any questions on things I've been saying there? Okay, so some of these same ideas of domain walls lie behind the calculations of entanglement entropy, but I'll describe the calculations in a more sketchy way so that the domain walls only come in a hand-waving fashion. So the particular calculation that I want to talk about is calculating the purity, that's the trace over states in some subsystem A of the reduced density matrix squared for that subsystem. Sorry, this well, this squared is under the trace, and then as I explained yesterday, the reduced density matrix for subsystem A we get by starting with some pure state and then pure state density matrix and then evolving with the block A time evolution operator for t time steps and then taking the trace over the subsystem that's complementary to the one that we're focusing on. And the calculation which I'll describe it just in terms of pictures, it is based on this early paper by Adam Nahum and his collaborators. So the pictures that I'm going to use are really very similar to the ones that Thomas Rosen has been using, but possibly some of my notation on slides is a bit different, so let me walk you through it. Okay, so what we need to do is draw pictures which represent different stages in this calculation, and the basic starting point, well, the most basic starting point is this initial state psi, but then we want to evolve it with third time evolution operator, and I'll represent that like this. So the state psi is represented by these black dots down at the bottom, and I suppose by drawing independent dots, I had in mind some unentangled initial state. So if you like, we could have spin up on all of the sites in this initial state, or we could choose some other unentangled initial state. And then we time evolve it, and I'm not drawing all of the details of gates here, I'm just representing the time evolution operator for some number of blockade time steps, or actually the calculation I'll describe is really for an evolution operator that varies randomly in time, so each gate will be chosen independently, and the whole time evolution is represented by the blue rectangle. Okay, so that's this component, and then we want to think about the density matrix for the state. So for that, we need something to represent the time evolved ket, and something to represent the time evolved bra, and that of course is represented in green here, and so there should be some more black dots at the bottom underneath the green rectangle representing this initial bra, and what you should notice is that the arrows coming out of the blue rectangle are oppositely directed to the ones that are going into the green rectangle. So that's signifying the fact that we've got a ket here and a bra there. Okay, so that's some diagrammatic notation for the whole density matrix, and if we start with a pure state here, then this is a pure state density matrix. So next we want to form a reduced density matrix, and the way we do that is by taking a trace over subsystem B, and we take the trace just by joining these lines. So the picture simply looks like this, and we've still got three indices on the Bra and Maquette within subsystem A. Okay. So that's the reduced density matrix, but now to talk about the purity, we need to take this, we need two copies of this, which we multiply together and then take the trace off. Two copies, we simply have a blue and a green rectangle twice over, and then doing a matrix multiplication for the two copies before we take the trace, that's connecting the lines that are coming out of this back blue rectangle onto the ingoing lines on the front blue rectangle, and then taking the trace is connecting the remaining legs. So diagrammatically, that's the calculation, and that's also the start of the next transparency. But now it's useful to reconsider this picture. So obviously it's an attempt to draw something in 3 dimensions, but if we now think how things look when we view it from the side, and when we consider things separately in region B and in region A, and the point is that the boundary conditions represented by how these indices are linked up are different in the two regions. So when we take that side view, then in region A, we're connecting the outside, the front blue sheet to the back green sheet. That's this picture here. And then the second and the third, green and black sheets are also joined together. Whereas in the region B, the front and the second sheet are glued together, and the third and the fourth sheets are glued together. And those differences matter when we think about doing the kinds of averages which I was talking about when I had the example of a single unitary. Because if we think about pairings, perhaps the case in B is the easiest one to start with, then the natural way to pair is as I've drawn here, because then when we sum over indices, we'll get the maximum number of free indices, and so we'll get the largest contribution in powers of 1 over q. And in a similar fashion, we want the kind of pairing that I've drawn on the left in region A. Okay, so obviously there are some details of the calculation which you'd have to roll your sleeves up and look at if you are actually doing it. But the principle, I think, is reasonably clear. It's that you have one kind of pairing in one region of the system, that is region A, and a different kind of pairing in region B, and there's some kind of domain wall between the two. Okay, is that plausible at the level that I'm describing things? Okay, so now the issue is, what are the consequences of that if you accept that this domain wall will have some statistical cost? Well, that domain wall, if we ask how it runs, it has to start at the upper boundary of the system, which is the time where I'm making these different pairings. It has to start exactly at the point in space where I've drawn the division between the subsystems A and B. But after that, it can choose whatever path will be whatever paths we like, and in fact we want to sum over all possible paths, but the ones that will be most important will be the ones that have the largest statistical weight, and the statistical weight is determined by the length of the domain wall. So saying that this domain wall, or entanglement membrane as it's called in this context, has a statistical weight per unit length, that's in the jargon saying that there's a line tension. And so if we're at short times, so this is the time direction vertically, if the time interval is short, then the largest statistical contributions come when we run the domain wall approximately along the time direction, and that means that the purity, the average of the exponential of the second Renyi entropy decays exponentially in time with some coefficient that depends on this line tension. But on the other hand, if we go to long times, then the domain walls that have the least statistical cost, well, again, they'll be the shortest ones, but now it's cheaper to go out the side of the system than to go out in the time direction. And if subsystem A is smaller than subsystem B, then it'll be cheapest to exit through subsystem A. And now the statistical cost will be, the purity will vary with the size of subsystem A, but it'll be time independent. So if you put those two ideas together, you get a result for the variation. Well, here I was talking about the variation of the purity, but if we want something like the second Renyi entropy, then we should take logs. And so the entropy of the subsystem increases linearly in time until you switch from this type of domain wall to the other type of domain wall, and then it plateaus. So physically, the idea is that when we start with the system in a pure state that's a low entanglement initial state, then under time evolution with this random circuit, gradually entanglement builds up between subsystem A and the rest of the system until the entanglement, the subsystem entropy, reaches a maximum value, and that will correspond to the value that it would have in an infinite temperature thermal state. Infinite temperature because in these quantum circuits, infinite temperature is the natural long-time state. And once you reach that entropy, then you use that. Okay, so that's, at least within this context, a nice and concrete calculation of one aspect of many-body dynamics. Okay, so then the final thing I want to talk about is operator spreading. And again, I can describe a calculation basically in terms of pictures, and the pictures are rather similar to the ones that Alexei Kitaev used, but because I'm talking about a system with spatial structure rather than the SYK model, the actual physical behavior that comes out and what we're interested in is rather different. So just to remind you of the basics, we're thinking of some local operator based at the point X, and we're time evolving it. Well, I've written Hamiltonian time evolution here, but what I have in mind, of course, is evolution with a random quantum circuit. And this operator evolves into something which we can write as a superposition of operator strings. And I'm using notation here, S for the different operator strings and S also as a label. So at a given time, I have amplitudes A labeled with S that are time dependent to have a particular string contributing. And I'll choose these basis strings to be orthonormal. I've left out a normalization constant from this trace. Choosing these to be orthonormal, then these amplitudes behave in the same way as amplitudes in the quantum wave function, in the sense that the sum of their modulus squared remains 1 at all times. Okay, so that was essentially what I talked about yesterday, and also what was behind Alexei Kitaev's discussions. But now it's useful to organize these amplitudes and probabilities that we get by taking amplitude squares in a particular way. So the basic point is that if we think of the set of all possible operator strings, then clearly there are a very large number of them, and they're pretty complicated. And what we'd like is some way of organizing them. And since, as I explained, one way of probing spreading of operators is via the OTOP, we'd like to organize these strings in a way that is relevant to a discussion of the OTOP. So the way that you do that is a bit different in a system with spatial structure to the way that you do it in the SYK model. But in a system with spatial structure, the aspect that we want to focus on is the fact that the strings in this sum typically get longer and longer as time goes by. So they spread out from the starting site, which is labeled by X. And the way to organize these contributions with that spreading process in mind is to sum the probabilities associated with strings which have a specific location for one end. And it's symmetric whether I think about the left-hand end or the right-hand end, but I'll focus in on the right-hand end. And so we can think of all strings that end at a given site in the system. So when I say a string ends at site k, what I mean is that at the sites k plus 1, k plus 2, and so on, I simply have identity operators. But at the site k, I have something other than the identity operator. So if it's a system with Hilbert space, local Hilbert space dimension 2, I have one of the Pauli operators at site k, and then I don't want to think anymore about what's at earlier sites k minus 1, k minus 2, and so on. So in order not to do that, I simply sum over all strings which have their rightmost operator at this site k. And this is well, it's a useful quantity to deal with because it will be relevant when we think about the OTOP in a way that's hopefully already reasonably plausible. And also, we have normalization still because if we sum over all possible values of k, then since every string must have a rightmost end at some unique site, when we sum over all values of k, we're completing this restricted sum with the prime here, and then since the sum over all string amplitudes squared is 1, the sum of these waves pk is also 1. Okay, so now the task is to think about how these weights evolve when we act with the random gates that appear in the random unitary circuit. Well, again, I'm following a description in a paper by Avi Mahmoud and collaborators, which came out at the same time as another paper by Kurt and Carty and collaborators. So again, I'd like to walk you through some pictures, and what I want to think about basically is the evolution of a string, or at least the part of the string that's near the end, when we go through, in fact, 1/2 of one time step with this random circuit. So when we evolve a wave function with a random circuit, we just act with a gate u, but of course when we evolve an operator, we have to act on one side with u and on the other side with the conjugate u dagger. So I want to use some notation for which operators are at which sites. I'll use this circle with a cross through it to mean that there could be any operator on that site, and the filled circle to mean that there's a non-trivial operator, and the identity to mean the other possibility. So this first symbol, the circle with a cross through it, is somehow the union of the other two possibilities. So let's think what happens when the end of the string is at one of these two sites. So if the string ends at site k, that's, say, we have some non-trivial operator on site k, and we have the identity operator to the right of it, so in particular, the identity operator on site k plus 1. Or alternatively, you could have the string ending at site k plus 1, and in that case, we have a non-trivial operator there, and it doesn't matter what operator is on site k, so I use this symbol. And of course, we could have strings ending at sites to the right of this, or sites to the left of this, but really my focus is going to be on how the probability to have a string ending at site k evolves under time evolution for this unitary circuit. So these are the only two cases that I'm interested in. And when you think about evolution, then there are two states that you can wind up with. So one is that nothing happens. That's what I've drawn down here. And the other is that the end of the string advances one lattice site, and that's represented by this picture. And you might say, well, why haven't I allowed for a third possibility? Clearly, on this site k plus 1, I've allowed all possibilities because either I have the identity or I have something that's non-trivial. But on this site, when I have the identity on the right, I've only included the possibility of a non-trivial operator. So I've ruled out the possibility of having the identity on both sides. And the point is that you can't get to a situation with the identity on both sides from this starting point. And you can see that most easily if you think about going backwards in time. So if I start with the identity on both of the sites, and I go backwards in time, which would mean having u dagger here and u there, then with the identity on both these sites, of course I cancel u and u dagger, and I just get back to the identity on both sites, which is inconsistent with my starting point. So these two possibilities are the only ones I can wind up with. And what I can imagine is that there'll be some probability to get to one of them, and a complementary probability to get to the other, and part of the task will be to work out what this probability is, and that probability will be a weight averaged over unitaries that I might choose for this evolution operator. So is it clear to everyone what I'm trying to do here? Okay, so that's one situation, and if I think about the alternative situation, then the final states that I want to think about are just the same, because I argue that these are the only possible final states. The only one that's omitted is one with the identity operator on both sides, but I can't get there by unitary evolution from either of these starting states. Now, you might imagine that the probabilities in the second case would be different from the probabilities in the first case, but it turns out that they're the same, and so I've used the same symbol here. So the only calculation that's left to do is to work out what this probability is, and I'm not strictly going to do the calculation, but I'm going to argue how it must turn out just from thinking about possibilities and arguing that they're equally weighted. So this repeats the pictures that I had in the previous slide, and if I think about probabilities, well, let me count the number of ways that you can arrange operators, either the identity or a non-trivial operator, on this pair of sites. Well, if I have the identity operator on both sites, there's only one way to do it. If I have the identity operator on one site and something non-trivial on the other side, well, since the local Hilbert space dimension is Q, the number of linearly independent operators is Q squared, but I'm distinguishing between the identity and non-trivial operators. So there are Q squared minus 1 non-trivial operators plus the identity. So there are Q squared minus 1 possibilities for this non-trivial operator. And in the same way, in this picture down here, we have Q squared minus 1 possibilities for the choice of this operator. And finally, if we have non-trivial operators on both sides, then we have Q minus 1 squared, Q squared minus 1 all squared choices. So when we think about the value of P here, so going from a particular choice here to something up here, then we have, well, we've got any operator on this site, so we've got Q squared possibilities, that's this factor of Q squared, and we've got a non-trivial operator on that site, so that's this factor of Q squared minus 1. And for any particular final combination of operators, in other words, if we specify specifically what operator is on this site and which one is on this site, so we might say that we have sigma x on this site and sigma z on that site, then then this is the number of possibilities, and what we can imagine is that any of those possibilities will be reached with equal weight, and the total number of possibilities is, well, if we have arbitrary operators on either of these sites, then we'd have Q squared possibilities on this site, Q squared possibilities on that site, so Q to the fourth altogether, but as I've argued, we can't get to the identity, so we've got Q to the fourth minus 1 possibilities altogether. So the idea is that to go from some specific combination here to some specific combination on the right, we've got this ratio of choices, and so that should be the probability of involving. And if you use the rules for higher averages that I talked about, you can confirm that that is indeed this probability. And then if you cancel things down, you come to that final expression for the probability that in this case the string advances by 1, or in this case that the string remains at the same site rather than retreating. Okay, so if you try and digest that, then basically what we're saying is that the end of the string undergoes a kind of random walk, and at this stage we're discussing things in classical language because that's all that we require. But it's a biased random walk, because the probability of advancing, that's P, is larger than half for any value of Q, and the probability of retreating, that's 1 minus P, is smaller than half. So, of course, the behavior of a bias classical random walk in one dimension is something that it's easy to understand. And what we want to think about is the probability distribution for the string to end on site k as a function of the site label k at different times. So the picture again is that we start with an operator at a specific site. So in that case, P is 1 on that site and it's 0 everywhere else. And then we watch how the strings evolve in length. And what that means is that this probability distribution gets broader and it shifts in time. And it shifts with some velocity and it gets broader with some diffusion constant. And the calculation that I outlined gives you the velocity and the diffusion constant in terms of the local Hilbert space dimension. Okay, so the final stage is to relate this to the spectral form factor. And, relate this to the OTOP. And basically the OTOP measures whether operators commute or not, and the operators will commute if the end of the string representing the spreading operator has not reached the site where the other operator is located. So if we have strings spreading from the point X, then this OTOP, in the notation I used in the lecture yesterday, will be given by the probability that the end of the string is somewhere to the left of the point Y. And if you, that means that in terms of these pictures, we locate the point Y on the k-axis and we integrate this probability distribution to the end of the string over sites to the left of the point Y. So that at any times, if the point Y is here, then when we integrate over this distribution, we simply get unity, and that's this early time plateau in the OTOP. But on the other hand, when we go to late times, if the point Y is located here, then the interval to the left of Y is simply 0, and that's the late time behavior of the OTOP. And when the distribution is passing past the point Y, then we're integrating over part of the width of this peak, and that means that the front broadens diffusively as a function of time, and the time at which the OTOP falls from 1 to 0 is related to the distance between the places in the system where the two operators are located, divided by a velocity, and that velocity is the one that's related to this probability P.
I don't see why this relation holds between the correlation function and the
Yeah, so we have we're trying to evaluate that. And then we decompose this into some strings with amplitudes which depend on time. And if then we have to think about a particular string and whether or not it commutes with this operator here. And if it does commute, then we can put the two operators y together, and for instance, if they're powers, they're square to 1, and if the string is a combination of powers similarly. If the end of the string is to the right of this operator y, then what we have to think about at the site y is a trace at that site of whatever the operator is in the string at the site y, and then over y, and then the operator in the string, and y. And you can argue that when you average overall the 4 possibilities here, in the case 2 equals 2, this would be the identity for sigma x, sigma y, or sigma z. When you average over these possibilities, you get 0. So what you end up with is either as of t squared if the end of the string is to the left of y, or 0 if it's to the right of y, and you have a sum over strings, so that reduces to some over strings that haven't reached y. Okay, so the significant part of this is arguing that this trace, once you average over the choices of this operator at y, gives you 0. And so the point is that if the operator here is sigma y, or the identity, then the trace gives you something positive, depending on normalization, let's say plus 1. And if you have sigma x or sigma z here, then the trace gives you minus 1, and the two things cancel. Okay, so that's really the outcome. That's really the result that we wanted. We've got a concrete understanding of how operator spreading works, at least in these random quantum circuits. So that is what I had prepared to talk about today. So to summarize the set of 3 lectures, I started out by talking about statistical properties of spectra, so random matrix theory and universal spectral correlations, and how they go in many body systems. And one of the points there from the first section of today's lectures is that there's a time scale which you could call a many-body Thales time, and it's only beyond that time scale that the spectral form factor follows the same behavior that you get from simple random matrix theory, and at earlier times you get deviations, but still those deviations can have a form that's reasonably universal in the sense of being characteristic of chaotic systems that are spatially extended in one dimension. I talked about the eigenstate thermalization hypothesis and how that links to statistical mechanics. Of course, I haven't talked about the eigenstate thermalization hypothesis in relation to quantum circuits, and the reason is basically that once you have unitary gates, then the behavior of matrix elements of local observables becomes rather trivial, and so there's not so much to say about that. And also, of course, if we're thinking about quantum circuits, then the natural long-time state is at infinite temperature, so the connection with statistical mechanics is not so interesting. And then in today's lecture, I talked about dynamics of quantum information, entanglement dynamics, and operator dynamics, and showed how you can do rather different but concrete calculations for each of them using random quantum circuits. And so I thought I should leave you with references to a few reviews which have a lot of the details of what I was talking about. So thanks very much.
This diffusive behavior of front chaos.
Yes.
This is for one-dimensional system, right?
Yeah, that's right. So in 2 dimensions, it's a different power. I think it's 1/3 rather than 1/2. And I think in higher dimensions, the fluctuations are even more suppressed.
And can we understand this 1/3 due to some relation to KPZ?
Yes, exactly. Yeah. Yeah. And that's worked out in the paper by Nahum and collaborators that I had on my slides.
Mm-hmm. Not seen. Thank you.
Okay.